So for those of us that don't know about simulation, I'm just going to give a brief introduction. So SOLIDWORKS Simulation helps SOLIDWORKS users introduce design validation early on in the product development process. Simulation uses the displacement formulation of the finite element method to calculate component displacements, strains, stresses from internal and external loads. So it offers an intuitive and easy-to-use interface that works in the same manner as you'd expect from SOLIDWORKS software. So it speaks the language of a designer with innovative features like the Analysis Advisor, smart connectors, and the Analysis Library. So some new enhancements in simulation in 2018 that I'm going to talk about today include the ability to import study features into assemblies, improvements to the pin connector tool, and some awesome enhancements to the stress Hot Spot Diagnostics Tool. So I am in a general assembly here, and I'm going to import some study features from some lower level simulations that I've done. So I can grab the study that I want to grab features from, and I can import features. So in this case, I'm going to grab the fixtures, but I can grab mesh controls, forces, anything I want, and they will have that imported annotation. So when you're working with those really large assemblies, that's really going to help speed up the process. So the pin connector tool now has the ability to grab more than just two faces of a pin. So previously, for this example here, I would have to use two separate pin connectors to hook this part together. But now, in 2018, I can grab up to 10 coaxial faces for my pin connector simulations. So the Stress Hotspot Diagnostics Tool was introduced in 2017. And what that does is that looks for a gradient of your stress values to try and find areas of interest in your simulation where the stress is really concentrating. So what's new in 2018 is the ability to refine the mesh in those areas and even run a singularity study and spit out a convergence plot. So we can see right here I had about 5-6 edges of interest, and one of those lines is veering off. So the more I refine the mesh, the stress is just exploding and diverging away from a value. So that's pointing to me that it's a mathematical singularity. My solution is not independent of my mesh. So previously, I'd have to make an Excel file with my successive runs and try and figure this all out manually. But now SOLIDWORKS can do that for me with just one click of a button. So that's a great time saver. Some other noticeable enhancements are the allowing the dismissal of warning messages. And that goes really hand in hand with email notifications for completed analysis. So you no longer have to worry that your simulations aren't running. And it really saves you from having to babysit that green progress bar. You can create results plots from imported data. You can have displacement control for nonlinear contacts, and a factor of safety plot for nonlinear studies. There are now also sensors for simulation mass properties. So a big part of simulation is the ability to optimize designs. Currently in SOLIDWORKS, there's only parametric optimization, which needs a lot of input from the user and is restricted to which parameters you select to optimize. So I have this hood mechanism, and I want to try to reduce the mass of this piece without compromising any of the connection points or the structural integrity. So I asked a colleague to try and optimize the design using the standard methods so I can compare the results to the new Topology Optimization in SOLIDWORKS 2018. This generative design process is going to determine geometry using the stiffness matrix of the FEA and give me some geometry that I really couldn't even fathom. So a topology study performs non-parametric topological optimization of parts. So starting with a maximum design space and considering all the applied loads, fixtures, and manufacturing constraints, the topology optimization seeks a new material layout. So the optimization will run to a goal, and it's going to try and find either the best stiffness to weight ratio, minimize the maximum displacement, or minimize the mass with a displacement constraint. It has some manufacturing controls, so you can control the thickness of the part, have preserved regions, demold directions, and symmetry. And finally, once you get those results, you have some nice export options as maybe a graphics body, a solid body, or even a surface body. So inside the software here, I've set up all of my constraints. I have some bearings and a force, and I want to preserve those regions. So this new part that I want to optimize, I want to make sure that I have this region controlled. So up at the top here where I'm connecting a bearing, that's one of my preserved regions. I have another bearing down here. That's going to be a second preserved region. And over here where I have an axle going through, where I'm actually loading the component, I have my third preserved region. So another manufacturing control I want to do is a demold direction. So this is going to mold together, and I'm going to define a direction of pull, and that's going to make sure that no undercuts get generated and I can actually have a castable part here. So the goal that I'm going to set for this is I want to try and minimize the weight. So this is going in the hood of a race car, and I need it to be as light as possible. So I'm going to try and reduce the mass here by 70%. So after I run this study, it's going to give me some pretty cool results. So the results that it's going to spit out are all based on the mesh that I defined. So we can see in here that it's fairly tessellated and kind of rough, but it gives me a really awesome insight onto where I need to keep my material to maintain the stiffness depending on the boundary conditions that I applied for this part. So I'm going to walk us through a case study that I did here. So the original part weighed about 167 grams. And when I ran the study with those boundary conditions, it had a factor of safety of about 3. So the part that I pawned off on my colleague to do the parametric optimization, you can see he got this nice kind of standard slot in there, and he reduced the weight by about 23% while still passing that load conditions. So this is the output from the topology study here. So I output it as a graphics body, and I use those techniques that Ryan showed us previously, and then I decided to 3D print it because I didn't quite believe how stiff it would actually be with how little material it has. But the software found where the stiffness was needed, and it maintained that stiffness really nicely. So then I did myself another case study for something a little more manufacturable. So something that I would CNC or cam out, and I reduced the weight by about 54%, and this is something that could be mass-produced and really functional. And again, I got the shape of all those cutouts and the shape of the design from that topology study, which would be something with basic intuition really kind of difficult to do. So SOLIDWORKS Flow Simulation is the other hand inside of SOLIDWORKS, and it's a general purpose fluid flow and heat transfer simulation tool. So it's powerful 3D design and CFD simulation tool, and it's an enabler for true concurrent engineering. So some of its capabilities are internal and external flows, laminar, turbulent, and transitional flows, rotating coordinate frames, incompressible and compressible fluids, Newtonian and non-Newtonian liquids, and of course, heat transfer simulation. So some of the updates to flow simulation in 2018 are the free surface flow. So that's like open channel flow, so water flowing in an open channel or a half full pipe. So it uses the volume of fluid method to find the surface interface between gas-liquid or liquid-liquid pairs. There's full templates now inside of flow simulation, and that will preserve all of your boundary conditions, your sources, and your goals, so you can easily replicate your studies across different models. And cyclic symmetry. So you can do those sector periodicity problems that include rotation and even heat conduction.